Consider this circuit where we have a power source, a resistor, and a capacitor. Okay, we are going to look at this circuit here in a simulation format. Okay, here we go. Now we have the power source, a battery, in this case a 9-volt battery, a resistor, a resistor that you have here, and a capacitor that you have here. Now I added a couple of things, an ammeter, a non-contact ammeter to read for us the current, and a voltmeter to read for us the voltage. And here's my switches. So initially the circuit is open, so we have no current, no voltage across the capacitor. I can measure the voltage across the resistor too, it would be 0 as well. Okay, I'll do it quickly. So this is the voltage across the resistor, so it is 0. The voltage across the diode is going to be 9 volts. Okay, now I place back my meter across the capacitor, and let's pay attention to what happens when we close the switch. Immediately as I close the switch, pay attention to the value of the current. Okay, you see it's a large value, that's diminishing. And notice what's happening to the voltage across the capacitor as well as the charge. There was no charge and it was building up. The voltage here is building up. The ammeter reading is diminishing. We are reading 0 right now with the precision of this ammeter. Finally, now here, the voltage across the capacitor is 9 volts, the same as the voltage that we had from the diode, from the battery. Okay, now the point I'm trying to get across here, I hope that you have noticed that the current is not constant. It changes as a function of time. Similarly, the voltage across the capacitor changes as a function of time. Obviously, the voltage across the resistor as well is going to be changing as a function of time, because the voltage across the resistor is given by Ohm's law, and Ohm's law is R times I. If I changes as a function of time, then the voltage is going to change as a function of time. That's what we are going to study in the next few recordings. Okay. Now to study it, let's apply Kirchhoff's voltage rule like we have learned to do. So we have one loop right now in the circuit. When switch S2 is open, it's like this part is not there. Now when it is not there, and if we take this loop starting here and going around, we have E going from here to here, then minus VR, and then minus VC, and we went back to where we started. Again, VR using Ohm's law is R times I, but because of the time dependence of I, we can write it as R times I of t. I as a function of t. Remember the equation for charge in a capacitor, Q is equal to CV. So the voltage across the capacitor is going to be Q over C. So my Kirchhoff's voltage rule changes into this. Okay, now from the rule we have this, what we had from the previous screen. Let's consider what happens on the onset. Just after we close S1, the charge in the capacitor was 0. If the charge is 0, and if we replace it in that equation becomes E minus I at time 0 R minus 0 equals 0. Let's call I of 0 I0, I sub 0. Then the equation reduces to this. From there, we solve for I sub 0. A long time after we close S1, as you have noticed, the charge is 0 and if we replace it in that equation becomes E minus I at time 0 R minus 0 equals 0. Let's call I of 0 I0, I sub 0. Then the equation reduces to this. From there, we solve for I sub 0. A long time after we close S1, as you have noticed, we are at a long time, the current is 0. We don't have any current anymore. So I, now in this equation, I at time, a very long time, let's call it I at infinity, is equal to 0. We are calling it I sub c here, the current in the capacitor, because that's the only current we have, but I is going to become 0. If I is going to become 0, then this part of the equation becomes 0. We are left then with E minus Q over C is equal to 0. And Q, we are calling it Q at infinity. So that's what we have. And Q at infinity is then just simply the voltage of the battery times C. The voltage across the capacitor is just the voltage of the battery. Like we have noticed in the circuit, it is 9 volts now. Okay? Now, so that's what we said. At time t equals 0, the current is what we call I sub 0. It is the voltage of the source over the resistance of the circuit. Long time after we close the switch, current is 0. Then the charge of the capacitor is voltage of the source times C. Now, what about in between times? What happens between here and here? Now, this equation, for the ones who are familiar with it, if you recall that I is actually a charge over time, for the ones who are familiar with calculus, it's actually dq dt, derivative of the charge. Okay, let's not worry about it here. But this is a first order differential equation. It's beyond the scope of this class to solve those kinds of equations, but we can provide the answer. The answer is this. For the charge, Q of t is Q infinity times 1 minus exponential minus t over RC. The current is I sub 0 exponential minus t over RC. Remember what I sub 0 is and what Q infinity is. Let's check out this equation to make sure we understand what's going on. At time t equals 0, E is what we call Euler's number. This is the inverse of natural log. Now, at t equals 0, what do we have? Q of 0, Q infinity, 1 minus exponential of 0. Exponential of 0, any number to the power 0 is 1. So that's going to be 1. So my answer is going to be Q infinity times 1 minus 1, that's 0. So Q at time t equals 0 is 0. That's what we have here. Now what about Q at infinity? Now Q at infinity is Q infinity 1 minus exponential of a number that's very large, minus infinity. The exponential of minus infinity is 0. So that leaves us with Q infinity. I can apply the same rules for current. At time t equals 0, then I get I0 because the exponential term is going to be 1. At infinity, the exponential term becomes 0, so I is 0. Okay? So the equations work. Now the other thing I would like you to pay attention to, the value of the voltage across the capacitor. What's the voltage across the capacitor? Vc of t is equal, remember for a capacitor like what we said in the previous screen, Q is equal to CV. So V is equal to Q over C. Oops. So V is Q of T over C. So it is actually Q infinity over C times 1 minus exponential minus T over RC. So we don't need to write a separate equation for the voltage across the capacitor because it's related to the charge. Okay, now we are fine with that. Okay, let's consider what does this equation mean? RC is the resistance, C is the capacitance. So when we multiply them, we get R times C, we get what we call tau, what we call the time constant of the circuit. It has the units of a time, and we call it the time constant. Now, if you notice, if we graph the charge as a function of time, it's going to look somewhat like this graph here. Now, when the time is equal to RC, when the time is equal to the time constant, then the exponential term is going to be exponential of -1. Now, if you calculate that, what you get is the amount of charge is going to be the total charge times 0.632. So it's 0.632 Q infinity, or about 63% of the maximum charge you can acquire. After two time constants, it's going to be about 87% of the most charge you can accumulate. So RC is somewhat of a measure of how long is it going to take to charge up a capacitor. Most of the charging happens, 63% of it, happens during the first RC, from 0 to RC. Okay, then the second largest part would happen during the second RC, from RC to 2RC, and then at the third RC, and so on. Rules of thumb. The capacitor is initially uncharged, it does not have a charge. The minute we turn on the switch, it acts like a wire, like it's not there at time t equals 0. But after a long time, okay, what do we mean it acts like a short circuit? The current initially is just the voltage of the battery over R. It's like there is no capacitor. Now, after a long time, there is no more current. So it acts like an open circuit. Like the circuit is broken, there is no more current through the resistor.